record now. Okay, so for next week, read chapter 7 in the book, and don't forget to turn in your assignments today at some point via Moodle. If anyone has any questions about the assignment, we can also go over that at the end of today's subject. Okay, I just want to move this. It keeps. I can't see my tabs. There we go. Heat transfer. Okay, so to follow up on our thermodynamics, we are going to talk about heating and cooling loads today and how they what's involved, what are the different parts. We're going to briefly go over how to calculate them, but my main goal is for you to understand the different factors that affect the heating and cooling loads. As a practicing architect, it is very unlikely you will ever have to actually calculate any, but it's important to know what things go into to affect the heating and cooling loads. Many of those things we've already talked about, in particular with glazing and solar heat gain. And we're gonna get into like the next level of detail today. So it's a pretty short lecture. It's a little technical, so I'm gonna take it slow. Let me know whenever you have questions. And then we'll have time at the end for assignment and psychrometric chart questions. So the big thing, why do we calculate heating and cooling loads? The most important reason is that it's necessary in order to put in the appropriate size heating and cooling equipment. We can also do it early on in design to look at different design concepts or materials that could create better energy performance for the building. Another reason to calculate heating and cooling loads is to look at the annual energy use. And this is particularly important these days, especially if you're going for a net zero energy design project. Factors that we have been talking about for the last couple of weeks that are part of calculating heat loads or cooling loads. We have our latent heat, that's our dry heat. That is what our thermometers, our thermostats will give us. And then there's a sensible heat, and that is from the humidity and either removing or adding humidity to the air. There's a couple of things that add a couple of items that add sensible heat into our cooling loads are people in the room, people, animals, pets, any animals, because we all breathe and we're breathing out humid air, and that adds a level of sensible heat to the load in the space. And there's one other factor. Oh, if there's a large humidity difference between the exterior and the interior, when you're looking at your ventilation, which is bringing in your fresh air, if it's much more humid on the exterior, when that ventilation air comes in, it could be adding humidity into your space, which is adding to your load. Now, there's a lot of equipment out there these days that can help prevent that additional load coming into your space. And we will briefly touch on those when we get to our active conditioning mechanical systems. So latent heat, sensible heat, U value. We started talking about the U value late last week, and then on Tuesday when we were looking at our assemblies and how heat is transferred from the exterior to the interior of our buildings. Conduction, that's heat moving its way through a solid material. Radiation, that is heat radiating off of a surface towards whichever direction is cooler. And then convection, which is heat transfer through the movement of air. So all of those things that we've been working on and learning about over the last couple of weeks are all of the parts that contribute to the heating and cooling loads of our buildings and of our designs. So stepping back for a minute and kind of thinking about it is like, okay, there's all of these factors affecting the space, but what exactly is the load? And there's 3 different types of factors. We've got heat gain or loss, cooling, or we have the loss or the gain, the load, and then also the extraction. So all of these different things are either being added to or subtracted from what the heating or cooling load is or calculates out to be. So for heat gain, we can get solar radiation that comes straight through the glass. We can get heat conduction through the envelope where the energy hits the outside of the surface and migrates its way and comes to the inside. We can get the heat generated within a space. That can come from people. And you can also gain heat through ventilation when you're bringing in your fresh air supply. For heat loss, if the climate or the exterior is colder in temperature than the interior, the conduction is going to go the opposite direction and come from the space and migrate through the wall assembly to the exterior. And likewise with ventilation, you could be losing heat from the space through the wall from the space through your ventilation system and losing heat to the outside. And again, these days we have mechanical ventilation equipment that does its best to minimize that heat loss or that heat gain with the ventilation, and likewise also with humidity. So for our heating or cooling load, you can think of it as the heat load is equal to the heat loss. So that's from the interior to the exterior. Heating is when we're trying to bring up the inside temperature to our thermal comfort level. The cooling load is equal to the cooling loss, but it has the sensible and the latent aspects of it. And keep in mind the sensible heat might have a thermal lag factor in as it's losing humidity. Excuse me. In this, if you have a cooling load, the sensible heat gain is from the exterior to the interior because your exterior is typically more humid than your interior. So in that case, it's a factor that you actually want to, I know it's the same, I guess, because your heat's going from the inside to the outside, but your humidity is going from the outside to the inside. Anyway, it has a thermal lag factor. Then there is heat extraction or heat addition. That could be from equipment in the space, such as a refrigerator, which is essentially like a heat pump, and it's taking all the warm air out of the interior of the refrigerator and putting it out into the room in the space where it's located. Mechanical rooms tend to get really hot, and these days IT rooms or server rooms, all of that equipment running, AV rooms, those also give off a lot of heat. They're not as bad as they used to be, and they keep getting better, but typically you need some dedicated cooling in a room that is full of equipment. So the main things that are affecting and used in the calculation of the loads is the area of all of the surface and the solar orientation, the U value for each type of surface. We touched base on that on Tuesday. We're going to look at it a little bit again today. The U value, remember, that is the conductance. So that is the heat that is conducting through the wall or the assembly. The outdoor design conditions, temperature and humidity. Indoor design conditions, temperature and humidity. And what that delta T is, what that temperature differential is between the interior and the exterior. So, quick recap, looking at a couple of different assemblies here by looking at all the various surfaces that you add up together to create your R value for resistance. The conductance value is the inverse of your R value. So if you go through the calculations, you look up all of the R values for your various materials, add them together, take the inverse, so 1 divided by 3.12 gives you the conductance value. And you'll notice that when our R value is poorly performing, our U value goes up, and when our R value is performing better, the U value goes down significantly. So those R values are the materials that you can look up in charts that say what that, so here's the R value. So we have our imperial units here, metric units here. This is what you want to look at is per inch thickness. If you have an uneven inch, you could calculate what that is. So at a 4-inch thick brick at a 0.2 per inch, your total is 0.8. And again, this is the R value, which equals the opposite of the conductance. That's what the 1/C is here. K is when it hasn't taken into consideration the thickness of the material. Okay. Notice over here, this specific heat, that is a factor of the material. It's the specific heat is it's called for calculations. Another thing it could be called in terms of architecture is thermal mass. That it's that it's the basic, it has to do with the material and what that material is composed out of, and it, at a chemical level, how well is that material going to contain a specific amount of heat. So it's like and then there's also specific heat capacity, which is, let's see, specific heat capacity. Well, you know, we'll get there later. Don't worry about it right now. Just know that this is unique to every material the same way that the R value is. And it's another part of what goes into the load calculation. Okay. Heating load is pretty simple. It's pretty straightforward because we're just dealing with dry temperature and we don't have to take into consideration the sensible heat. The other thing is when we have a heating load, we are trying to keep, the load occurs when outside of our space or our building, the temperature is cooler. In that condition, the conductance of the energy inside the room is always going to be trying to go outside. That's the nature of equilibrium. The hotter it is, it's trying to migrate to where it's cooler. So in heating load conditions, you do not have to take into consideration the solar orientation because you know that the outside is already cooler and that any solar gain that's hitting that surface is not going to try and migrate into the space because it's cooler on the outside. So if heat hits a brick wall and even what's absorbed, that conductance is still going to go back to the exterior and not to the interior. So in this condition, solar orientation is not important. The inverse is that when we talk about cooling, solar orientation is a big factor of calculating a load because you have that added, not just temperature differential, but that added solar radiation that's hitting your wall assemblies or your roof assembly. So our sensible heat load is based on area times conductance and the temperature difference. So net area times conductance times delta T. So again, that's in feet squared times BTUs per hour per feet squared per degree times our delta T. So what's going to happen here is the square feet are going to cancel each other out. The degrees are going to cancel each other out. And what you get left over is BTUs per hour. And again, that's written as BTUH, but it is BTUs per hour. And that hour is at the bottom of the fraction. So this is why you guys are going like, why is she always going off about what the units are? Because if you think about it, if you get confused and you can't remember what is how to do the calculation, you keep in mind what are the factors that you need to look at to know what your load is. Okay, it has to deal with the area times the conductance times the temperature differential. Okay, so the area and the temperature differential cancel each other out to leave just BTUs per hour as the load. So in addition to our building is losing heat to the exterior where it's colder on the outside. In addition to that, with our ventilation, we have the air load, which is our rate of ventilation, which is measured in cubic feet per minute, CFM, that's air movement, times the outside air factor times the temperature differential. The outside air factor is essentially the same thing as a conductance value, and it's based on, it's a set number, and it's based on the specific heat of air times how dense it is. The only time that this would ever change is at extremely high altitudes where the density of the air is significant enough to be a lot lighter, less dense. Higher altitudes, the air pressure is a lot less. So if you were to go practice in probably Denver or I think Mexico City is pretty high too. The mechanical engineers there would be using a different outside air factor for calculating an air load. So heating, pretty straightforward. We're just dealing with dry air. We have our building envelope and we are losing the heat from the interior to the exterior with all of our surfaces. So that is our walls, our 4 walls, picture box, our roof, which is the 5th plane, and our slab underneath the building. Don't forget about that. All right. This is what is a broken down calculation of how to calculate a heat load. Again, pretty straightforward, very simple. You look at the indoor temperature, the outside temperature, what that difference is, that's our delta T. So our difference is -66. Okay, it's really cold outside in this example in Missouri. So winter heating condition. We look at all of the surfaces, the windows, the walls above grade, the walls below grade, because chances are the construction materials are going to be different above and below grade. The roof, the outside air factor, and the basement floor or our slab. In San Diego, we do a lot of slab on grade construction. If you don't have slab on grade and you have a crawl space or an unconditioned basement, what you would be calculating is the transfer from the interior through that built up flooring to the airspace down below. And in that case, you have to look at what your air temperature would be in the airspace, not necessarily your exterior temperature. And then basically you add them all up and that is your load. So 920,410 BTUs per hour. Does anyone remember how many BTUs are in a ton? Nope. It's 12,000. Yep, and that's a factor of the ton is based on that old original calculation when they used ice for cooling, and it was how many BTUs it took for a ton in weight of ice to melt over 24 hours. So 920,410 divided by 12,000 is 76 tons. This is a really big building. This example is. Okay, the point in showing you this calculation is to give you a picture of adding up the various factors that are affecting the load. Okay. Cooling gets a little bit more complicated because of the moisture impact. So it's the same factors as in heating, except we have to add in the latent heat. So when we were talking about latent heat a little bit ago, I was mentioning the internal gains from people, oh, okay, well, this is all, the people here is what will give the latent heat, and then the equipment, your refrigerator, lighting can add a lot of heat to a space. That adds up to be the sensible internal load, plus the outside air factor from heat gain. So you're going to have, if you're bringing in warm air as fresh air, it's going to have some humidity to it, and it's going to have some heat in it. So, I'm sorry, heat is a sensible, latent is the humidity. Typically, when you are cooling, the air inside has less humidity than the outside hotter air. If it's not, you can get conditions of interior condensation, which you really want to avoid. So you still add up all of these different factors. You add up the sensible loads together, you add up the latent loads, and then you add them both together for the total load. But keep in mind, as we saw when we were looking at that Title 24 example, knowing the difference between sensible and latent is important for sizing your air conditioning equipment, because not only the equipment will be rated in what it can handle, both for sensible and for latent. Not to scare you, but just to show you how more complicated it starts to get to calculate the sensible load. Starting at the top, we're looking at our indoor and outdoor conditions. Outdoor temperature, 94, indoor, 74. That's a 20-degree delta T. Outside, the wet bulb temperature is 75. Inside, they're looking at just the relative humidity. If the wet bulb temperature outside is 75, and the dry bulb is 94, we know that the relative humidity is going to be less than 100, but it's not needed for the calculation, so they didn't bother to fill it in. So here's where the solar exposure starts to come in, is when we're looking at the building envelope, and you have to start looking at the orientation of your surface. So you still have your area, and you still have your, I forget what TLF is, but this is your conductance, but it's also, you have to start taking into consideration the solar heat gain factor and the solar coefficient. This is different from the solar heat gain coefficient, which is what's used for glazing. But we're not gonna get into that, but just understand that the cooling load is affected by the solar orientation of each facade. So then there's transmission. So they've pulled out where there's, oh, excuse me, I'm sorry, they broke this down. This is where they are adding in the U value. So it's all three of these, and I apologize, but it's all three of these that give how much solar heat is hitting the outside of the building. So then we've got our transmission is how much heat's going to come through. Transmission's not a good word, because it should actually be it also involves conductance. And this is where they've added in the roof area. Then we've got the outside air infiltration and that load. This is just the sensible load here. Then we look at internal heat gains, people, how much heat we are giving off to the space, lights, equipment, appliances, and then our latent load calculation down here at the bottom. People, 500 people at how many BTUs per person. Diversity. Anyway, you don't have to calculate it, but just the important thing is to know that it's the people plus the outside air, and that's where that outside air humidity comes into play. So a lot more complicated. We got a lot more factors going on. So the key things to remember are we've got the heat gain coming through our windows. We've got the heat gain from the envelope. That comes from the fenestration, opaque surfaces, and the roof. Don't forget your internal gains for affecting the cooling load. Then your outdoor air factor. Okay, so like I said, not long, but there's a lot of information here. And again, my goal is to help you keep in mind all of the different things that are affecting our building performance through heating and cooling loads. I think this is going to be like the shortest lecture all semester. So are there any questions?
I think I had a question on the assignment.
Okay. I will bring that up. Any questions on heating and cooling loads right now?
I think I missed, you were saying something about the inverse of the conductance.
Mm-hmm.
You were saying, I didn't understand what you were saying, to be honest with you.
Okay.
What to do with the R value?
So R value is resistance. The opposite of resistance is the conductance, or the of how much heat's coming through a wall assembly. So R is resistance. It's resisting heat coming through from one side to the other, and that's and you calculate the R value by looking at all of your different materials that are in your wall. Okay, so in order to find out what the conductance is, it's the inverse of your R value. So this is letting heat in. This resistance, I can use my little annotate, my little drawing button. So this is resisting heat from coming into the building, and this is what is bringing heat into the building. And so that's why the, and I know it's confusing that they call it the U factor. So U factor, it's the conductance, it's 1 over R, but the concept is, it is what is allowing heat to move from one side of the wall to the other, creating that, actually in this case, for a heating load, it's going out through the wall. For the cooling load, it's coming through the wall. Because in heating, the exterior is colder, and in cooling, the exterior is less. Okay. Alethea, did that answer your question?
It does. Thank you.
That was yes?
Yes.
Okay. Okay, any other questions on heating and cooling loads? Okay, I'll bring up the assignment and we can talk about questions on the assignment as soon as I learn how to use my mouse properly. Oops. Yes, here we go. Queer drawings. Okay, who was it? Isabel? I didn't see the face with who was
Oh,
talking.
no. It's me, Priscilla.
Priscilla, okay. What was your question?
I was just wondering on number 8.
Mhm.
I was reading, going through the PowerPoints, but I don't know if you said it during the lecture, but I don't recall about that.
Okay. This is exactly what we were just talking about. Conductance is also the U factor. It's also 1 over R. What is the inverse of conductance? If conductance is 1 over R, what's the inverse of that?
So R over 1?
Exactly, but when you have 1 as a denominator, you don't need to put anything down. It's just R.
Here. Okay. Cool.
Is
All right.
it, I guess I realize I'm using math terms here, inverse or reciprocal. Is
No,
that,
yeah.
was that, is that confusing?
No, I get the inverse.
Okay, all right. And I admit that it's confusing about conductance has so many different ways to write it. C, U factor, 1 over R. Yep. Okay, I know there's some questions about the psychrometric chart, which I'll go to next, but does anyone have any other questions before we jump on that? Not yet? Okay. So, psychrometric chart. Key things to remember: dry bulb temperature is along the horizontal, and that is that's the same thing as latent heat. The humidity ratio is going vertically up the right-hand side. The curved lines are the relative humidity levels, and the diagonal lines from upper left to lower right are wet bulb temperatures. And when you get confused, just take a minute and look around the chart, and a good one, and I try to use a good one, will always label what an example of one of those lines are. So we got wet, this is 85-degree wet bulb temperature, and we've got 10% relative humidity curve, and this says dry bulb humidity ratio. And let's talk about air temperatures. The higher the air temperature, the more moisture the air is capable of holding. The colder the temperature, the lower the total amount of humidity the air can hold. So at 0 degrees, and this is Fahrenheit, actually let's look at 30 because it's close to 32, which is freezing for us. The air can only hold, so we look at, I'll use my circles again. At 30 degrees, you go up to, just use the vertical lines are there, and the vertical and horizontal lines are just to help you maneuver around the chart. What you want to read are the curved lines or the diagonal lines and the numbers at the bottom and on the side. So at 30 degrees Fahrenheit, the maximum amount of humidity, this is 100% humidity saturation at that temperature, is going to be about right here, which I would just say is about 25 pounds, grains per pound of dry air. And that's just how they measure the humidity. So freezing, almost or just below freezing at 30 degrees Fahrenheit, the maximum amount of moisture is 25 grains per pound. Now, if we go up to 90 degrees, oops, let's undo and go back to circle.
How's it going, guys?
Good. Who was that? Not important? Okay. You guys can still hear me, right? Nods? Okay, I see Mars nodding. So at 90 degrees, let's see, actually that's off the chart. I gotta go down. We'll do 75 degrees, that's a good one. So 75 degrees at 100% humidity. You follow the vertical line up. Here we go. We hit 100% humidity. The wet bulb temperature is 75. And the amount of moisture, the maximum amount of moisture is just barely over 130 grains per pound of air. So there's a big difference between 25 and 132. Okay, now I hope you've noticed that the 100% humidity wet bulb temperature is always equal to the dry bulb temperature. That's at 100% saturation. And there was a really good question last week about this. 100% humidity saturation does not mean that it's raining though. Okay, it is not the same thing. Rain is a factor of the climate and the weather, not of the current conditions. Well, I guess if it's raining, like it's raining where I am right now, it is a current condition, but they're different. Weather does its own thing in terms of thermal comfort. It's a different subject. Chances are current temperature and humidity can affect the weather, but I'm not a meteorologist and I don't know a lot about that. So wet bulb temperature at 100% humidity equals your dry bulb temperature. Concentrate on your diagonal lines, your curved lines, and your horizontal and vertical values. The straight lines and the vertical lines within the chart are just to help you be able to read it a little bit better. Okay, so going over that again, is that helpful in clarifying the psychrometric chart?
Yeah, that's helpful.
Okay. Just as a recap too, that we're looking for our thermal comfort range, which is generally, this chart's not showing it, but it's generally between 70, maybe 85 60, right about 50% humidity. If I could move this up, I might want to move this up just a little bit. So we got 70 to 85, around centered about 50% humidity. This is sort of like the sweet spot of thermal comfort. And then ranges outside of it can go a little up, a little down. A good point that our textbook makes is that with passive systems and natural ventilation systems, instead of just following the ASHRAE guidelines for heating and air conditioning, assuming that you're going to be climate conditioning your building 24/7, as people, we are actually able to tolerate a little bit more in certain directions if we're not in 100% climate controlled conditions. The other factor is that people, based on where they're from and what they're used to, can be more sensitive to humidity or heat or cold. I think I used the example of an Indian woman I worked with who grew up in Mumbai, which apparently it's like 110 and 90% humidity there 80% of the time. And she was in San Diego and was always cold. And here I am. I'm a transplant to San Diego from New England, and I think it's always warm and wonderful here. So that can really affect a person's sense of thermal comfort also. Okay. We went over the assignment, talked about some questions, psychrometric chart. We did heat transfer today. Talked about our loads. They're all drawings. And you are going to read, yes, don't forget to read for next week, chapter 7. We just did the two most concentrated amount of like scientific and building envelope stuff for the whole semester. So we've just gone through the worst of it. Everything after this, it's gonna be a lot more fun. So good job. This is why I do it at the beginning before you guys are completely exhausted and you're not all caught up in your studio projects, although 3 weeks in you probably are. Passive systems, super fun. The chapter in the book, it's pretty lengthy. They go into a lot of detail, and we'll be touching on a lot of different systems. So, but it's cool stuff. Okay, that's it for today. Short Friday. Does anyone want to stay after? Any questions? Tech stuff? Are there any tech issues still going on? Okay, I'm going to stop recording, get this up on the website, and stop.